Okay. So we're going to go ahead and start off with some just basic theory about pipelining. I think what is a pipeline and how is it different from single cycle and multi-cycle structures for programming. The example that they give in lecture is like a drive-through. So since we've already done that one, I had to come up with like a new analogy. This is a pancake buffet, like a breakfast buffet. You've got the station where you take your plate, and the station where you take your pancakes, and the station where you take your bacon, and then where you pay for all your food, right? So a single cycle processor is where we have your first person in line. In this case, it just happens to be Abe Lincoln. So he would get his plate, and then he'd get his pancake, and then he would get his bacon, and then he would pay for his food, and then he'd go to his table. And then once he's completely finished, then it is Francis Bacon's turn, who is the next person in line. So this is analogous to like the first instruction, getting the instruction and then reading from the registers, and then like doing an ALU and that kind of thing. So the issue here is that Abe Lincoln gets his plate and then he moves on to the pancake, but now the whole like plate taking station is completely open. So why not just have Francis Bacon start on that stage and get his plate while Abe Lincoln is getting his pancakes? And then they each move forward and get their next. Abe gets his bacon, Francis Bacon gets his pancake, and then Julius Caesar, who happens to be third in line, can get his plate. So this is analogous to each of the instructions, just taking up a different area of the pipeline processor at each time in different stages, so that we are like maximizing the number of instructions going on at once and minimizing our CPI as low as possible and the amount of time. It is important to note that even if like Abe Lincoln is vegan or whatever and he doesn't want bacon, he still has to be at that station. So even if he's not using all of the information, the instruction isn't using all the information there, they still have to take out that spot, take up that stage. They're not allowed to skip or anything like that. So he still has to be at the bacon taking station before he can move on, and everybody will move in line so that we have like everything in the processor being used at all times. So this processor is going to look somewhat like this. This is pulled straight from the processor simulator that they give you in the EECS website. So you're definitely going to want to check that out. I think I put it in links and resources if you really need it. It's really similar to the processor that you're actually going to be programming, but there are a few key differences that I'm going to draw after I go over a big part of theory about the pipeline processor. So there is, hopefully I'm not going too fast. I probably am, but it's okay. There's one issue in translating this processor into C++, and that has to do with these registers right here. So in a normal register, it will like hold some value. This is supposed to represent a register. This is going to be like pink on the inside. That's awful. You know what? It's good enough though. So this register is going to hold some value, like 10. And it's going to be outputting that value to whoever might need it in these wires. So maybe the ALU, or it's an address, anything like that. But then coming into it is going to be a new value. And this new value could be like 9. So when we activate the clock, when it is, so it's like when the clock is either, when the clock is moving from off to on right here, then we are going to update all of the registers at the exact same time to equal the value that is going into it. So here it'll stop being 10 and it'll become 9. And then because this relies on some register before, it'll change to some new value, 6, whatever, anything like that. So this way, all of the registers will be activated simultaneously and be set equal to the value immediately before them. Unfortunately, there's no way to simultaneously do anything in C++ because it all has to be done in like steps. So the way that we translate this in C++ is instead we have I'm just gonna Clear this frame. We have our old register that equal 10. This is our regular state. So this is state. And then we have a new state over here. And at the beginning of every cycle, the state and the new state will look exactly the same. But during the cycle, you will only ever modify the new state. So the value going into this register is 9. So in the new state, we're going to change this to equal 9. And then we will do that for every register. That way we still have the info that we need from the first state, but we can change it in the new state. And then at the very end of the cycle, we will set the state equal to the new state, essentially saying that we've moved forward one cycle. This is basically just to make up for the fact that we can't simultaneously change all the registers at once. This is the closest that we're going to be able to get in C++. So you will only ever modify new state, and so new state will only ever be on the left side. We'll just write this out. I think they do have this in the spec. It's good to reiterate. New state will only be ever on the left side, and state will only ever be on the right side. So this is saying you're taking information from the state and moving it into the new state, and then at the end, you will go ahead and overwrite what you had in the state with the new stuff. So that's how a register is going to work in C++. There are a few changes that are different between the pipeline simulator that they give you on the website and the pipeline that we are going to be programming in Project 3. The first one is that there is no mux in the ID stage, so this isn't here anymore. And instead, it will get moved into the WB stage all the way up here. And this will come from like the instruction and both the instructions, and then that will equal your new destination. That will make sense. That will make more sense when you actually start programming that. But there's no mux here anymore because there's no longer a destination register in each of these. The second thing is that there is no equal register in XMEM, this guy right here, which is weird. I kind of find this odd because you do need an equal register. My solution was to just create one, like externally. So I added this on my own, not as part of the XMEM structure or anything like that. Other people have just used the ALU result as the EQ because you're not using it if it is a BEQ. So one way or the other, you're going to have to create or reuse something for the EQ register. And it's not going to appear in the source code that they give you. There's also one more full register line at the very end. This is called the WBE end. You know what I mean? The WBEND register. And this is just going to take whatever comes out of this box right here, so that you can use it for forwarding. Some of the forwards will have a full 3 stages needed. So you're going to need this stage to hold the information at the end that's write data. And that's already implemented for you as a structure. You just got to make sure that you use it. Essentially because the explanation that they give is that there's no forwarding done in the register file that there is in the processor simulator that they give on the website. And then the last change between these is that this mux is actually not in the WB stage anymore. It's in the one right before it. This is a pretty small change. It just means that the ALU result and MData get muxed here and go into a new register called, this is getting really messy here, so we're going to move it up here. This is your write data register. So those are the main changes between the simulator that they give you and the one that you're going to be programming. It's really only 4, but that means that when you're debugging, you should really go and check the processor to make sure that your program is running it the exact same way that the processor does. I do have notes for what each of these stages does, But unfortunately, I think like part of the project is being able to look at this processor and turn it into instructions that you could program in C++. So I think even though they're a bit ambiguous as to what they want you to do in all cases, it's good to just try it on your own, see what you come up with, and then ask on Piazza and Discord when you reach an ambiguity, because there are quite a few, and it's better than doing trial and error. But when you're debugging, the handiest thing that I found, I spent far too long doing trial and error and debugging by comparing what I got in my final result to the processor. So you'll notice some patterns really quick. You just want to compare each of these color-coded sections to the section in the simulator. So you'll quickly check like, okay, PC equals this PC, and I'm gonna go ahead and get and then the greens, the instruction should equal the instruction, PC plus 1 equals the PC plus 1. These 4 numbers that you'll see right here should equal these 4 right here. And you'll quickly compare just to see if anything's different. There are very few cases where they should be different. It really only happens when there is a hazard that you need to deal with, because the simulator and the program deal with one of the hazards slightly differently. Normally, if they look the same, it's totally good. And if they look different, then you either have a bug or it's like, it doesn't matter if they're different. One of the main differences.
I have a quick question.
Go for it, please.
Can you go back to the slide right before this one?
Yes.
So is the purpose of the WD stage just essentially for data forwarding, so to just make our life easier when it comes to dealing with hazards?
Yes. Yeah. Okay. So you'll want to hold on to this data so that you can pull it all the way back and put it into this mux right here. I think normally it just like, I'm looking at this to see if there are any hints, but I can't see any. I think normally it just takes this write data earlier and puts it into the register file early, so that you don't need to do this extra step. But we're not doing that. That's too much work. So instead we're just going to have another register that will bring it all the way back into these muxes.
Awesome. Thanks.
Yep, that's a really good question. Thank you. So that's the main goal of the processor and comparing it to your code. You're going to be doing it a lot if you want to make sure. Going to make sure I'm not missing anything here. I think that's the goal of that. I think this is just like a helpful little key to make sure you're comparing the correct parts of your output to the output of the simulator. So that is the basic pipeline. What we're going to do next is the hazards. And this is a big topic. So if anybody else has any questions about pipelining, now would be a good time to ask, because hazards is like more than half of the project.
I did have one small question, actually.
Mm-hmm.
So I was looking at least through the version of the data path as appears in the lecture. So there was one specific mux that I wasn't entirely sure what to make of it. Okay. So specifically, it's in the execute stage.
Okay.
So in the execute stage, there's a mux which compares what I believe is register B and the offset. So
right.
Yes, that one. Yes. So I was wondering what the purpose of that mux is, because it appears that the ALU is only meant to be used for primarily things like adding and ignoring.
Right. So the reason that you need that ALU is for LW and SW, or this mux is for LW and SW. In those, you're actually adding the value of register A to the offset to get the address, the memory address that you'll use in data memory. So this is when you do LW 5, 4, and then like 16 or whatever. This is adding the 16 to whatever is in whatever value is in register 5. This got really tight really quick. So for add and nor, you would just do the value B, but for LW and SW, you need to use the offset. Does that make sense?
Okay. Yeah, that makes a lot more sense now.
Okay, cool.
I guess one last question I had.
Go for it.
So there's two extra smaller muxes inside that same execute stage.
Mm-hmm.
So those two muxes don't actually appear in the lecture version.
Oh, good catch. Yeah.
I was wondering what those two muxes did, since the lecture obviously doesn't mention them, since it doesn't appear there.
Right. Those are our forwarding muxes. They take information from future stages so that you can resolve any data hazards that you might have. So the orange comes from the ALU result, and the purple comes from data, and then the green one, which we're adding, is coming from write data in the new register that we're adding in our project. So those are for forwarding, and you can get them in the simulator by selecting like the data forwarding option in the bottom right corner. I can't remember exactly what it's called, but they won't appear first. You'll have to make them appear.
Ah, I see. Okay, that makes sense now. Thank you.
Yep, you're welcome. Any other questions before we move on to hazards? Because they're big.
I have a
Quick question about the destination.
Yep.
Like, we don't have them because, is it because in C++ we're, in all our structs we have the instruction already?
Yes. So I'm going to go ahead and
Oh.
replace, that is a good catch. Instead of OPs and all of these, we have instruction. So we're carrying over the entire instruction into every register. So by the end, we'll already have the stuff that we need for destination, and we'll just do the mux there instead.
All right, so we don't have to like carry it over because it's already being carried over.
Correct. Yep.
All right,
As
thanks.
part of the instruction. And I heard,
question on the field functions that are given in the project
go ahead. Yep.
in that starter code. So are those the actual values of the registers and the offset, or is it like just the actual register and the actual number of the register?
I can't quite remember which field registers you're talking about.
This is field 0 and field 1.
Oh, okay. Parts of the instruction. Yeah.
Mhm.
So in the instruction... Okay, then one more time. Now that I know what you're talking about, could you reiterate your question, please?
Sure. So are I guess fields 0 and 1, are they the actual values of reg A and reg B? Or are they just the numbers like of the registers, like register 1 or 2?
They would be the numbers. So this would be field 1, or field 0, and this would be field 1, and this would be field 2.
Okay, cool.
Yep.
Thank you.
You got it. For some reason, I could not remember seeing the word field in this project ever. Yeah, that makes a lot more sense now.
Cool. Thank you.
You're welcome. All right, I'm going to move on to hazards. So the thing with hazards is they tell you, okay, for the second half of this project, you're going to want to resolve the hazards. You say, okay, what hazards? And they say, the hazards. Make sure you do all of them. And you're like, okay, well, how many are they? And they're just like, oh, you just got to resolve the hazards. So I got kind of tired of that, and I've color-coded the hazards. And here they are. I've colored them is based off of a traffic light, actually, because I think it really helps me remember what each of them is, what each of them do, whatever. At the bottom, we're going to start at the bottom. This is with your data hazards, code green. So when you have an add whatever into some register R, and then you have another instruction immediately after that uses that R, or later, doesn't have to be immediately after, then this R is not going to be set in the register file in time for the future registers to use it. In our pipeline implementation, this is going to have a range of like 3 instructions. So if any of the next 3 instructions, 1, 2, 3, use the register that is like your destination register, then essentially you're going to have a data hazard. This is a code green. You're going to want to go forward some information from future stages to resolve the data dependency. This is for adds, nors. I think it's just those 2. I can't remember the exact details. But there are 5 conditions that you'll need to look out for to determine if you need to call a code green and forward information from a future stage. So you will, I might need to pull up my notes for this one, because I don't think I kept them. That's unfortunate. I used to have notes on where you would check for a code green, but I don't have them. That was poor planning, but that's okay. So code green is just forwarding information from a future stage back so that you can use it quickly. And then there's also a code yellow. This is the only stalling that you will be doing in this program. It is when you have an LW blank R, because R is your destination register, and then you are using it in the instruction immediately after the LW. This is because the LW actually doesn't get the information that you need in time for the instruction immediately before it. If you had an add followed by an add, and there was like a dependency between them, then you would pull back this ALU result into whichever of these two muxes that you needed in order to resolve the data hazard. But for an LW, you don't need the ALU result, you need the stuff from memory, and you don't have that loaded until the very end of the stage. So you need to put a no-op in between them so that nothing is going on in the EX while the LW has time to pull the information from data memory. Once that's done, it just becomes like a code green, and you can pull information from your write data in the memwb register back into the mux. So code yellow, if you have an LW directly followed by a dependency, then you need to do a single stall. Stalling means that you set the IDEX register to be a no-op, so that it doesn't do anything, and then you will prevent these first two registers from, is that right? Yeah. And then you will prevent the first two registers from updating the next cycle. That way you'll have a gap, and you won't need to worry about that. You know what I mean. I'm starting to lose my train of thought. The last hazard that you're going to need to look out for is the big code red. This is only for BEQ. This means essentially that you are branching, and you're going to check for this in the mem stage right here using your EQ and checking if the current instruction is a BEQ. If both of those are true, then you need to set, making sure. If both of those are true, then you need to set all three of these to no ops, essentially like stopping Q. That's why it's a code red, stopping all of those instructions so that they're no longer executing and they can't write any data or anything like that. And instead, you're going to be changing the PC to the new target branch, and then you'll be starting back up with the new instructions at the new location that you've just branched to. So you'll be checking for this in the mem stage. Make sure you don't check it in the EX stage, because that was a mistake I made. Check it here. And once you've done that, change the PC and change all three of these to no ops. I think that's all you need to.
Sorry.
Yep, go ahead.
Would you mind repeating the two things you check for again?
Yes. The two things you check for are if that equal register that you set up earlier is true, and if the instruction in mem is a BEQ instruction.
Cool, thank you.
Cool.
Just to clarify this, because we are assuming that we are not taking the BEQ.
Correct. That's a good, thank you. We are assuming that we are not taking the BEQ. We're speculating that we'll probably just be continuing on after this. We only need to call a code red if it is true that we're actually branching somewhere else. And that's when we'll squash all of the previous instructions and start where we left, or start at the new location. So those are the 3 types of errors.
I have a quick question
Yes.
about yellow. So, could you sort of repeat when we determine that we have a load dependency, how exactly it works that we can just add a no-op without it sort of fucking up whatever instruction was in that stage? Does that question make sense?
Right. I think that does make sense. I'm going to take a bit of thought. You're going to be checking for it in the IF stage, or I think I miswrote that. I think it's supposed to be, yeah. You're going to be checking it really early.
Oh, okay.
As soon as you get the instruction, if the next one is an LW and there's a dependency, then you're going to overwrite this guy, right? Nope.
Right.
You're going to be overwriting, I was asking myself that. You're going to be putting a no-op in the IDEX, overwriting whatever just got carried into here. And you're going to be stalling everything so that it doesn't move forward next time.
So then, essentially, your PC isn't supposed to increment so that it'll just push that instruction that was sort of delayed.
Mm-hmm.
Is that correct? Okay.
Yep, you won't be doing anything here. You'll basically just have, like, if you are not stalling, then do this stuff.
Okay. So then, just to make sure that I get this, if we have our load in the IDEX stage and then the previous instruction in fetch, and we determine that there's a dependency with fetch and load in IDEX, we would just be stalling the PC and inserting a no-op, right? Is that essentially the process?
I'm just thinking. I think you've got the right idea. I think the detail that we need to look out for, I'm going to have to answer this afterwards because I have to look at my own code now to figure out what I actually did here. This is definitely this is a lot more to like take in all at once and keep in mind. So I understand where you're coming from. I think you definitely have the right idea. Just need to make sure I know which registers you're checking the instructions of.
Yeah, you're good.
Yep.
Yeah, no worries. I'm just wondering about the process, essentially, is what I'm questioning. Okay.
Oh, hello. Yes, I will watch that later. I don't know if that appeared for you guys. I got a notification.
Is anyone else going, or can I ask a question now?
I think you can go ahead.
All right. So for the code red option, the BQ one, in the specific case where a programmer and where the BQ statement routes to the option for not taken, would that still count as a code red?
Yes. If it just went on to the next instruction, it would still count as a code red. It would slow the program down for seemingly no reason. But that is an optimization that you do not need to make, which means you do not need to include it.
All right, perfect.
Yep. So it would still count as a code red. You only need to check if code red if equal, and it's a BEQ instruction.
All right, thank you.
Yep. I think I saw that on Piazza too, so that's a good question. No extra optimizations. These are good questions. Does code green make sense to everybody? I think there were because there haven't been as many questions about it. So it sounds like it's hopefully a bit more sensical than the other two. Okay. I think that was 30 minutes. So this should be a good time to wrap up. I usually stall for no reason. So I'm going to make sure I hold myself to wrapping up on time and within a reasonable amount of time. That is the outline for the project and helpful color coding for all the hazards so that you can use that to refer to them instead of whatever nonsense we were trying to use before. Thank you guys so much.
Thank you. This is super
Thank
helpful.
you.